In the episode on independent behaviour, we saw that individuals rationally and naturally take selfish actions. They behave in ways which produce the best outcomes for themselves. In this episode, we will see that collective action can emerge from the interaction of independent individuals, and that collective action can have properties which are different than the properties of individual action. We'll use agent-based models to synthesize interaction and see for ourselves what collective action emerges. 2,500 years ago, Aristotle said, "In the case of all things which have several parts, and in which the totality is not, as it were, a mere heap, but the whole is something besides the parts, there is a cause." In modern systems language, we would say that the properties of whole systems emerge from the interaction of the parts and are different than the properties of any of the parts. The cause which Aristotle was talking about is emergence. To clarify what emergent behaviour is in systems and what causes it, we'll look at some examples. Examples of independent agents interacting, and then we'll see how the whole system behaves. We'll begin with birds. We know that nearly all birds can fly. We also know that some birds, but not all of them, fly together in flocks. In flocks, it looks like the birds are cooperating, that they're communicating in some way and making shared decisions about what to do together and then doing it, but they're not. Flocking is an emergent behaviour in a bird flight system. Each bird is following a simple set of innate behavioural rules, and when they interact, the behaviour that emerges is flocking. This type of emergent behaviour is common to many species: fish shoal, cattle herd, and penguins huddle. A second example with humans as the agents is traffic. Traffic is an emergent behaviour of cars being driven by humans on a road. Just like the birds, humans follow a simple set of behavioural rules. We don't intend to create traffic, it's the result of individuals acting independently and interacting with each other. One undesirable property of traffic is the traffic jam, something none of us would deliberately create. Agent-based modelling uses computer applications to synthesize the interactions of independent agents over time and model what emerges. The inputs to the model are behavioural rules, and the outputs are visual and graphical images of the emergent behaviour. The models that we will use are implemented on NetLogo, a programming tool authored by Yuri Walensky at Northwestern University, CCL, Illinois. The first model is flocking. The agents are birds following three innate behavioural rules. Fly in the same direction as nearby birds. Get close, but don't get too close. The birds are not randomly flying. They are not cooperating either. They are reacting to the actions of the other birds. On the left of the screen are the input settings and controls, and the output is the black square which represents the sky with small arrows as the birds. Clicking on Setup randomly places the birds in the sky. Clicking Go sets them flying, and they follow the three behavioural rules. What emerges from the interaction of the birds when they follow these rules is flocking. The second model is traffic. In this model, the interaction rules are even simpler. Slow down if you get too close, or speed up if there's room between you and the car in front. The drivers are not randomly driving, they're not cooperating, they're simply reacting to the actions of the other drivers. With 10 cars on the road, everything goes well, a smooth traffic flow at top speed. With 20 cars, a traffic jam forms, and no one goes faster than half speed, even though if they behave differently, there's no reason why they could not continue at full speed. If everyone just stops braking hard, then eventually we get back to a smooth flow at top speed. With 30 cars, the traffic jam forms again, and this time reducing the level of braking doesn't fix the problem. The only thing that works now is external intervention to reduce the speed limit. This model explains the theory behind managed motorways. Agent-based modelling has many applications across all the sciences. Our particular interest is in sociology, the interaction of people in societies. Our first example of social interaction is segregation in urban populations. People living in clearly identifiable groups with a shared characteristic. The rules are very simple. People are happy when they have a minimum percentage of people like them living around them. They move if they're unhappy, and they stay where they are if they're happy. At low levels of desired similarity of 10%, the start point is an average similarity level close to 50%. This is no surprise, as there are equal numbers of only two types of people randomly dispersed. There's very little movement, everyone is soon happy, and there is no sign of segregation. The average hardly changes, is now just over 50%. Increasing the happiness level to 30% results in clear patterns of segregation emerging, with everyone surrounded by an average of more than 70% of similar people, far more than the 30% needed for everyone to be happy. Segregation emerges even though that was not the intention. With higher satisfaction levels, it takes longer for everyone to be happy, and the outcome is almost complete segregation, with segregated areas surrounded by unoccupied properties. Segregation is not a consequence of people only being happy when everyone around them is like them. Segregation is an emergent property of rational behaviour by reasonable people. There are a number of agent-based models which synthesise human behaviour in crowds, similar to that of birds in flocks. One interesting model with some surprising results is known as heroes and cowards. In this model, people are distributed randomly in a room. They are either heroes or cowards by nature, and they follow some simple rules. Identify a friend and an enemy. If you're a hero, protect your friend by getting between them and their enemy. If you're a coward, protect yourself by getting your friend between you and your enemy. What happens depends entirely on the starting position, and the results can be fascinating. One possible outcome is known as the slinky. The crowd forms itself into a line and moves around the room in a procession. Another possible outcome is called the yo-yo, similar to the slinky, but the line moves back and forth along one edge. With another starting position, the crowd can end up forming into a spiral in the centre of the room. Finally, everyone can end up frozen to the spot and not knowing what to do next. None of these outcomes are intentional or the result of cooperation. The patterns simply emerge from following the behavioural rules from different random starting points. We can also use agent-based models to synthesise evolutionary traits in populations. The example we're going to use is similar to the share bluff problem that we solved using evolutionary game theory. A population of cows has two traits, considerate and greedy. The cows follow some simple rules. Move around and eat the grass, If you're a considerate cow, don't eat the grass down to the ground. If you're a greedy cow, eat all the grass you can. The fitness for survival benefit is the grass as food. The cost for being greedy is that the grass doesn't grow as well and there is less to eat. If the benefit of being greedy and eating more grass is more than the impact on grass regrowth, the cost is less than the benefit, and the outcome is a population of greedy cows. If the benefit of being greedy and eating more grass is less than the impact on grass regrowth, the cost is more than the benefit, and the outcome is a mixed population of greedy and considerate cows. These are the same outcomes that we would have predicted using evolutionary game theory. What agent-based modelling shows us is that when individuals interact, their actions and reactions result in collective action which is different from any of the individual innate actions. There are things which are necessary for collective action to emerge. There must be continuous interaction between individuals, and individuals must be aware of the actions of others and react to those actions. Individuals must follow innate behavioural rules. There are some things which are not necessary. There's no intention or collective purpose needed. There's no communication or agreement required. And there's no central authority, coordination or instruction required. What we can take away from this episode is that in general, the properties of a whole system are different from the properties of the parts of the system. The whole is not the sum of the parts. In particular, the properties, characteristics and attributes of a social group are additional to, not an addition of, the properties, characteristics and attributes of the individuals in the group. In the next episode, we'll build on what we've learned from this episode and the episode on independent behaviour to see how a combination of rational, innate, learned and emergent behaviour can help social species to survive.